Hi, I'm Professor Goins. In this video, I'm going to introduce the concept of a directional derivative. Okay, so I have a surface given by z is equal to f of xy. On that surface, I have a point P, and at that point P, I'm going to attach a unit vector. And the unit vector can go in any direction. And suppose I want to find the rate of change of the surface or the slope of the surface in the direction of u. And again, that u could point in any direction we want. As long as it's a unit vector, we can find the derivative or the rate of change in that direction. So the formula that we're going to use to compute that rate of change is the following. The notation is given by capital D, so D for the directional derivative, and then a subscript u, so in the direction of the vector u of the function f evaluated at the point P. So the left-hand side just tells me what I'm computing, the directional derivative of f in the direction of u at the point P. The right-hand side tells me how to evaluate this. The way we evaluate it is we find the gradient of the function. We evaluate the gradient at the point P, and then we take the dot product with the vector u. Okay. So this right here is the formula that we will work with. Now, a quick comment on the notation. I'm actually using the point P two different ways there. So the point P here refers to the point on the surface, which would have the coordinates A, B, or well, it's three coordinates, right? It's in three space. So this would be A, B, Z. A would be, the first component would be an A, the second component would be a B, the third component, Z, would be the function evaluated at A, B. And I'm also using it over here, P, as an input for the gradient of the function. So the function has inputs x and y, which means that the gradient would have inputs x and y. So I'm also using the point P to denote the input AB. So this is also the point P here. So based on the context, it should be clear, am I referring to the point on the surface or the point in the XY plane? Again, it should be clear from the context. Okay, so let's compute some directional derivatives, and let's start with an example that we can graph relatively easily. So let's look at the function f of x, y is equal to, I'm sorry, f of x. Let me think if that's the one that I want. Yeah, no, that's fine. F of xy equals 1/2 y. First of all, let's look at the graph of this, okay? So the graph of f of x equals 1/2 y. Again, as the equation, I can rewrite this as z equals 1/2 y, or equivalently 2z minus y is equal to 0. And so in this form, we see that it's the equation of a plane. So it's a pretty simple surface. And let's see what the equation of that plane looks like. As a reminder, this is the x-axis, the axis coming out of the board. The plane that represents the board itself would be y, and then z. So z is the vertical axis. Okay, so if I wanted to graph z is equal to 1/2 y, where this would be like your input, your output, so this is your horizontal, which is your input and your output. That means that within the yz plane, the graph of this equation z equals 1/2 y would look like this. Basically, think of that in the xy plane. The graph of y equals 1/2 x, and we see the slope of the line in through the origin slope 1/2. And then, of course, that plane comes out of the board, so it's going to look like this. Okay. Hopefully that, I'm not an artist, but hopefully that makes sense. What I want to do is let's pick a point on the the surface, let's say this point right here, and let's say that corresponds to the point where x is 3 and y is 4. So I'll write the point P is equal to 3, 4, and again, that would be the point in the xy plane, but it's also a point on the surface if I add the z component to it. Okay, so let's compute the directional derivative at that point on that surface in a variety of directions. For part A, so let's say find the directional derivative. At that point, using the following unit vectors. Let's say A, the unit vector is going to be I. B, the unit vector is going to be J. C, the unit vector is going to be given by root 2 over 2, root 2 over 2. Okay. Let's use this in a second. Nope, not enough. Sorry about that. So solution. Well, I erased it, but let me go ahead and put that formula back up here. Okay, so for part A, okay, so compute the directional derivative of this function, which has this surface, and the direction of I. So in other words, for part A, we are going to be going in the direction that is perpendicular to the YZ plane. In other words, going along the x-axis. Okay? So this would be all right, so the right-hand side, compute the gradient. So remember that the gradient of a function is a vector, and the corresponding components of the vector would be so the first component would be the partial with respect to the first variable, the second component would be the partial with respect to the second variable, so on and so forth. In this case, I've got a 2-variable function, so it's going to be a vector with 2 components. The first component is the partial derivative with respect to x, which is 0. The second component will be the partial with respect to y, which is 1/2. We evaluate that at the point P, and then take the dot product with the specific unit vector, which is I. Since this vector is a constant, evaluating at the point P gives me that constant vector. I, again written in component form, will be 1, 0. Dot product of those two vectors would be 0. Multiplying corresponding components again gives me 0 because there's a 0 in the first slot and a 0 in the second slot. So that tells me that the slope of this surface in this direction is 0. And that should make sense because that's going to be just a line that is, again, parallel to the x-axis, which is going to be kind of slope 0. Part B. Okay, so let's compute the directional derivative in the direction of j of the function f at the point P. So again, it's going to be the gradient of the function evaluated at P. Now, let's look at our work in part A. The gradient of the function was given by the vector 0, 1/2, evaluated at P was 0, 1/2. So that part of the computation is going to stay the same, so it's still going to be 0, 1/2. And then I take the dot product with the vector j, which in component form is 0, 1. And then you take that, again, evaluate the dot product, you get 1/2. So that means the slope in the direction of j, which would be this direction here, well, it's the slope of the line, right? So it's going to be the slope, starting from this point here, looking in the y direction, it's going to be the slope of the line, which is 1/2, and this has slope 1/2, so that should make sense. Part C. Okay, so in this case, we're taking in a direction, I'll illustrate here on the diagram here in a moment. Directional derivative of the function in the direction of root 2 over 2, root 2 over 2. Once again, the first part of the computation remains the same, and then this would be root 2 over 2, root 2 over 2. Dot product would give you 0 times root 2 over 2 is 0, plus 1/2 times root 2 over 2 would be root 2 over 4. So that would be at the blue dot if I look in the direction. So this is in the direction of 1, 0. Let me grab a couple of markers here. Let's see if I can do this with two hands. The black marker would be coming out of the board, so that's the vector I. The red vector would be the j vector, so that's going in the y direction. The vector we just did, root 2 over 2, root 2 over 2, will be the one that splits that in half. So I don't know if you can see that or not. Let me just do this vertically for a second here. So it'd be this vector right here, where the black one is I, the red one is j, and the blue one would be root 2 over 2, root 2 over 2. So that would be at this point here. So we're looking in this direction. So notice that it's not quite as steep as looking up the line, and it is more steep than looking in this direction. Okay, so it's somewhere in between. We could also do one last one for this video. Let's call this part D. I think this would be good to look at as well. Let's say u is equal to negative j. So if u is negative j, that means I'm standing at this point P, and I'm looking in this direction. Well, if I'm at the point P and I'm looking in this direction, in the positive j direction, the slope was 1/2. So what do you think it's going to be if I look in that direction? Okay, let's verify if your guess is correct. So let's see, what can I clean up here? I'll clean this part up right here. And we'll just replace A part D. Okay, so part D. So we're looking at the directional derivative and the direction of negative j of the function f at the point P is given by the gradient that we just computed, which for all of these is 0, 1/2, dotted with negative j, which is 0, negative 1. Evaluate the dot product, we get negative 1/2. So if I'm standing at this point P and I look in this direction, my slope is negative 1/2. If I'm standing at this point P and I'm looking at this direction, my slope is positive 1/2. So that's the concept behind a directional derivative. I can compute the slope at a point in any direction. I just have to have a unit vector going in that direction.